Well, we finally made it. This is the last episode dealing with the fundamental forces. In this episode, episode 10, I'm going to be talking about the electromagnetic force and its involvement with the creation and also the emission of light. Now, a few things, housekeeping. One, I'm not going to say electromagnetism again because it's too long of a word, so I'll be using EM instead. And then when I use the word light, I'm going to be using it in context of radiation because they are the same thing. If I say radiation, I'm talking about light. If I talk about light, I'll be talking about radiation. They're equal. Also, I might slip in an energy in there by accident. So if you hear those three terms, they're all exactly the same thing. So we'll get that established. Now, in this episode, I'm going to be talking about EM in context of our solar system, primarily the sun and the earth. It applies consistently across the universe in terms of how it behaves. It's different based on the situation that it's operating in, but the bottom line is EM is always involved with the creation and also the emitting of light. Got that down? Perfect. Now, let's look at some fun facts about the sun, about the EM, and about light. We'll start off with our sun. Now, our sun, if you know anything about it, essentially it's just one gigunda ball of ionized gas. And when I say ionized gas, I'm talking about plasma. We've talked about plasma before, and you can think of it as like this soupy, thick, charged environment. So that's fair enough, in terms of describing it. It gives you the vibe of what the sun's all about. In terms of what the sun is composed of, it's 75% hydrogen, 24% helium, and 1% these odds and ends type of elements. There's iron in there, for example, and there's silicon in there, and just a few other things that make up that 1%. And then on top of that, this plasma contains electrons. And they're just not plain old electrons. They're free electrons. Now, what's the difference? What are we talking about here in terms of being ionized in these electrons? So first off, the sun is extremely hot, and the pressure is just unbearable due to its strong gravity. So what ends up happening, this plasma that makes the sun, which by the way, the sun, there's no solid matter with the sun. It's gas. And to give you a perspective of how big it is, if you take 1.3 million Earths and you put them together to make this oval shape, round shape, that's how many Earths they're required to compose one sun. It's big. In the whole scheme of things, it's not the biggest star in the universe, but it's big nonetheless. So anyway, back to what I'm talking about here. In terms of these electrons and this ionized gas, you have to realize that what's happening due to the pressure and the heat, the hydrogen and the helium and all the other small amounts of elements that are in there, it's so miserably hot in there that the electrons, you can think of them that they're claustrophobic. Normally we talk about them in context of being inside the atom, outside of the nucleus. But here, they just can't take it anymore, and they just escape, and they leave the atom. So what ends up happening, you have these free electrons, they're out there in the plasma, and the hydrogen and helium and these other smaller amounts of elements, they're hanging out in that plasma without the proper number of electrons. And because of that, they are called ions. So you see a bunch of ions and you see a bunch of electrons. Now, due to the heat and the speed, the heat and the pressure of the sun, these things are zipping around at a rapid pace. Electrons and ions, and they're going everywhere constantly. They're going at just a tremendous amount of speed, which takes you to the fact that when electrons are present by themselves, they exert an electric field. Now, when they're moving, there's a magnetic field. Now, you look at this in context of the sun, how big it is, high temperatures, strong pressures, and those electric fields and magnetic fields they're staggering. And we'll talk about that in a little bit here. So, got that out of the way. As you can imagine, you're well aware of, the sun is our solar system's furnace. And it uses helium and hydrogen as its fuel, like you may use propane or electric or methane for your power in your home, for example. It uses helium and hydrogen, and we'll get into that here shortly also. The sun is comprised of 3 zones, that being, and all 3 of these zones, they all are plasma. The inner part is called the core. The outer part zone outside of the core is called the radiant zone, and outside of that is the convection zone. Now, I won't get into the details of each of those. I will get into the core here shortly also. There's a lot of things I'm putting off here. But the bottom line is, what I want to bring up is that these zones are not rotating the way you think they're rotating. If you grab a basketball and I spin it, and it's on my finger and the ball's spinning on my finger, it's not doing that. Each of these zones are rotating on their own terms. So it's this weird thing that's happening on the sun from that standpoint. Additionally, in the convection zone, the equator, it rotates differently than the poles do. So there's this funky rotation dynamic going on there. And I'm going to throw another one. We'll get to that shortly also. In terms of, if you haven't figured it out by now, because I probably mentioned it 5 times already, the EM emits all light, period, in the universe. And our solar system is no different. There are 7 types of light. Also, you probably have heard them referred to as, surprisingly, radiation. And these are radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. Now, the difference between those 7, it deals with the wavelength in terms of the intensity, the frequency of that light. In other words, a radio wave is pretty benign, and they're big, and they're minding their own business. Gamma rays, on the other hand, are really intense, they're vibrating fast, and they can cause a tremendous amount of damage in things that they hit, in particular if they hit us. All right, got that? As I mentioned before, radiation is light. Light is radiation. And both of those are comprised of photons. Photons are particles they're fundamental particles that were formed during the Big Bang. So they've been around a long time, and anytime there's light involved, there's photons involved, same with radiation. The obvious question that I've always had is, if these 7 types they're considered different types of light, why do they all have different names? You have radio waves, you have rays, you have X-rays, and then you have some light. But why? Because people like confusing us. That's why they give different names, and they make it as confusing as possible because they just like making it confusing. Essentially, all of the light that we experience on Earth comes from the sun. Now, we are getting other light from outside of our solar system, for sure, but it's an infinitesimal amount, and you can just consider all the light that we experience, the sun originated it. So we're good there. With the sun, our go-to source, let's stroll down memory lane as to what actually is happening on the sun. In other words, what we want to find out is, the sun is emitting all this light / radiation. How is it doing that? What's the engine behind that? And the engine is nuclear fusion. And nuclear fusion occurs in the core of the sun. And let me give you a very basic explanation of what actually is happening. Now, as you may remember a few minutes ago, I talked about the plasma, and that basically because it's so hot, we have these electrons that are free electrons, and they left the atoms of helium and hydrogen. Well, what ends up happening is if you look at a hydrogen atom, just the most common type of hydrogen atom, it has one proton in the nucleus and one electron. Well, if basically that electron leaves and becomes a free electron, that proton essentially, that hydrogen atom is essentially just a proton. It is what it is. So with that said, what happens in the sun, because of the pressure from gravity going on, you have the EM force involved there, you have the strong nuclear force involved, you have the weak nuclear force. Basically, you have all the forces involved in this process. But what happens is you have a hydrogen atom, which is a proton, which is, again, the most common type of hydrogen, in the universe. Because everything is moving so fast, the electrons and all of the hydrogen and helium atoms are flying around within the plasma. These protons, two of them collide from time to time. And time to time, I mean constantly. It's a never-ending process. And when they collide, they fuse together and they form a new version, basically an isotope of hydrogen. And this version of hydrogen is very rare, but it has a different makeup of protons and neutrons in it because of the collision and fusion event that happened. Then what happens is that rare hydrogen, because it's flying around all over the place, plasma, because of the heat and pressure, it collides with the most frequent type or most common type of hydrogen atom. They collide and fuse together and form another atom. And this is an uncommon version of helium. Then two of these uncommon helium atoms, they end up colliding and they create a form of helium that is the most common helium in the universe. And as a result of doing that, they basically spin off two protons as a result of that. And because those two protons are back out into the plasma again, the whole cycle can start again. So it's this never-ending cycle of these collisions and fusion going on. So you say, okay, fair enough, I see that. Now explain to me, how is that creating energy? So what ends up happening is when the strong nuclear force is involved, and it's always involved at the atomic level, that implies that there's going to be a lot of energy. So you have a collision and then a fusion, and that resulting atom from the fusion is really, it doesn't contain all of the parts from the other atom, and it has to get rid of that energy, the extra energy, and also the energy resulting from the collision, and off it goes in terms of energy. And that energy, light, radiation, it's all the same again, that is what is being put off by that nuclear fusion event. So you see, it's fusing, the nucleus coming together, that's the tie behind it. So anytime you hear that about a strong nuclear force and there's collisions and fusion, you better run for the hills, because there's going to be a tremendous power from that as a result of that. It's sort of weird because you think about atoms, they're very small, but yet they can put out like power that you can't believe because of the strong nuclear force. It just wants to hold them together, and when they collide, that strong nuclear force just lashes out and just puts out all of the light/radiation. Now, the sun's been doing this for 4.5 billion years, and it's going to continue doing it for another 5 billion years until it slows down. I'm going to let this helicopter pass. Now that we've established that's what is happening in the core of the sun, which is emitting radiation. And by the way, that radiation are really the intense radiation types, that being gamma rays and X-rays. Just get that established. Now you may be wondering, okay, I understand that it's creating all this energy, gamma rays, X-rays coming out of the core of the sun in that plasma, because there's particles flying everywhere and electrons, and it's a mess in there. But what I haven't mentioned is, so that's nice, but how does the EM, how is it involved with that process? I mentioned at the beginning, the EM is central to the generation of light. And you're one step ahead of me, because that's what I'm going to talk about right now. There are 4 areas, if you look close enough, within the sun that are sort of giving you clues as to how the EM gets involved. Now, we can think of it, it's sort of like a search for, like, where's Waldo? You're sort of trying to find where this EM is, like we're trying to find Waldo in one of his books. So let me go through all 4 of these to give you a feel for how the EM is involved with the generation of light. So looking at the nuclear the fusion event, the one thing that's happening is these protons repel each other, just like 2 ends of a magnet, positive ends of a magnet. They're repelling each other. They just don't like each other. They only like, the negative only likes positive, but positives don't like each other and negatives don't like each other, and they're always repelling each other. And as a result of that, the repelling of those charges and those protons, but the gravity is trying to push them together, and the strong nuclear force is trying to hold things together. And you have this crazy thing that's going on until gravity in the core of the sun, because it's so great, it collapses those together. So if you think about it, the EM is pulling them apart, and when they do collide because of gravity, this results in even a stronger collision and fusion, which makes just more energy. Number 1. Number 2, where EM gets involved, when these X-rays and gamma rays are basically leaving the core from the nuclear reaction, what's happening is they're going out into the plasma, and they're impacting all of the particles and ions, being electrons, out in the plasma. Because of that, it's oscillating and accelerating the electrons and the ions, for that matter, and from that it creates a tremendous amount of magnetic fields. The strength of the magnetic fields are just tremendous. So as you can see, what ends up happening is, because X-rays, gamma rays are hitting those particles, they're moving faster, they're generating energy, and from that they also emit light. That's number 2. So that's the second area where the EM gets involved. The third area is a really strange area. As I mentioned about the zones, they're rotating differently. When the zones rotate differently, what ends up happening is they end up twisting and tangling the magnetic fields. It gets really sort of funky. And when those fields get twisted, it messes with the plasma, and it creates both sunspots on the sun and solar flares. Sunspots are the magnetic, basically those fields within the plasma, they get so funky and twisted that radiation, and that being the bad radiation, X-rays and gamma rays, leave the surface of the sun, that being the plasma. On top of that, it also causes the atmosphere around the sun, the plasma, to emit gamma rays and X-rays also. So that's that weirdness of the magnetic field, which is a part of the EM, that creates that type of energy. Now, those can be pretty nasty, because what's happening is, and I might as well get into it right now, when nuclear fusion occurs within the core of the sun, What ends up happening, it gets scattered out into the plasma, but from the time it's originally formed within the core, it takes 100,000 years for that light from that nuclear event to come to the surface of the sun, to be emitted out into space. What ends up happening is, because the plasma is so thick, it's emitted, the gamma and X-rays are emitted, but it gets absorbed back into the plasma, and it's remitted back out, and it's this never-ending, it's a cycle that goes over and over and over again over 100,000 years. And by the time it gets to the surface of the sun, it's been diminished in terms of its strength, that light. So instead of it being X-rays and gamma rays being sent out into space, what's happening is it loses its oomph. So basically it's sent out as visible light or ultraviolet light instead, and that's what we experience. Got that? So what ends up happening as a result of that is the radiation that's coming from that, in terms of us, is less in terms of the intensity, and it causes less damage to us. Now, what's really weird about this is our atmosphere, believe it or not, assuming that gamma rays and X-rays do come out, and this is why I want to get back to solar flares. When solar flares, because it's happening on the atmosphere, those rays are reaching Earth, and they can cause damage to satellites, with astronauts or on the International Space Station. It can cause problems with them, because we don't deal with radiation that well at all, not being gamma rays and X-rays. As a matter of fact, our atmosphere has the unique ability to let the more benign light sources types come in, like ultraviolet and visible. But our atmosphere does not let gamma rays and X-rays in. So basically it absorbs those and it scatters them. So it's not something we deal with every day, except again, regarding sunspots and solar flares. Those X-rays and gamma rays do come this way when those occur. The last area where the EM gets involved is really the centerpiece of how the EM plays a part in radiation, light creation, and emission. Of the four fundamental forces, the EM force is the only force that has the ability to carry light through space. The EM is pretty much an infinite type of force. It can go on forever. Gravity is an infinite force, but it doesn't deal with force. It deals with space-time. And the strong nuclear force and the weak nuclear force, they are dealing in the atomic level in a small area. So they can't do anything in terms of being a carrier for light or radiation. But the EM is that force. So as you can see, anything that comes from the sun, whether from the nuclear fusion event, from the domino effect of it hitting the electrons and these ions, and it's putting out energy, or dealing with sunspots or solar flares, the EM, they're hitching a ride on the EM for it to come our way. So in other words, if the EM was not around, the bottom line is we would not receive any light from the sun, because there'd be no way for that light to get here. So anything that the sun would create, it would stay local to the sun. And as a result of that, our Earth would be a little bit cold, and it would be very dark, because we would get none of those type of lights. It's a wrap. We're done. So in summary, no EM, no light. Done. Next episode, I will talk about electrons, because I've talked about electrons a lot over the last so many episodes, but I really haven't talked about the details of electrons, and it's pretty amazing. So anyway, I will put that together, and I'll talk to you. Bye.